All right. Thank you, everyone, for joining today. We'll quickly get started. Well, we're happy to have you here and appreciate you taking the time to join this talk. Before we begin, let's take a moment to reflect on the land that we are on and its history. We acknowledge that the land that we are meeting on today is the traditional territory of many nations, including the Mississaugas of the Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples, and is now home to many diverse First Nations, Inuit, and Métis peoples. We are most grateful and respectful for the use of this land. It is my pleasure to introduce our speaker for today's session, Dr. Yury. Thank you for joining today. Dr. Yury is a professional geoscientist currently applying expertise in geochemistry to mineral exploration projects. Based in Whitehorse, Yukon, he examines the intersection of geochemistry and environmental sciences, in particular how permafrost degradation destabilizes northern environments. The session today is about the permafrost paradox, from natural barrier to toxic, unstable ground. You're all encouraged to keep your videos on, engage, and feel free to ask questions during the session, either by raising your hand or putting it in the chat. Thank you for joining today, Dr. Yury. We're excited to learn from your work. Please take it away.
Thank you. Um, Before we begin, there's one thing I need to emphasize that there are many flavors for the earth sciences. I'm a geochemist, but this topic is predominantly a main focus for people who are working in superficial geology. So there are some areas that I do know, but I'm not claiming to be an expert on this thing. I just very interested in this, and well, right now I'm living in a place that actually have quite a lot of permafrost, so I decided to take the opportunity and use it and study it a bit. So before we begin, there's a quiz I wanted to start right at the title essentially, and that is what do you think, guys, is the permafrost is actually made of, despite the fact, well, yeah. So I just shared the link in the chat. And the question is, what's the percentage of the permafrost is actually ice itself? So I'm going to give it, I don't know, probably 15 seconds. It should be working if I'm not messing up the tool. Oh, yeah. Yes, so the tool is active. So I guess another um, 5 seconds and we go with the day with this particular one. Okay, so here are the results. And the answer to this particular question is that it varies greatly. The ice content in permafrost can be ranged from 5% to over 80 or 95. So I guess I'm going to keep the pool on for now. Yeah, so, but what is actually a permafrost? Permafrost, by definition, is the ground that remains frozen throughout the entire year for multiple years. And some of its layers can actually melting at the top, start melting. Also, as we go deeper in the ground, there is some natural increase in temperature. So there is upper and lower borders where the ice is kept. Well, permafrost is frozen. So thickness varies greatly and continuity also varies. And the Northern Hemisphere, we have quite a lot of it. And Canada, well, have very extensive permafrost developed through its territories. One thing I would note about this particular illustration is that the purple region here is indicating the continuous permafrost, which means that it's just the layer of it present through the entire area shown here. And one interesting fact that I was also interested to find out was that this particular piece, this is the permafrost that's present beneath the sea, so below the seafloor. So we rely on the ground for the infrastructure, and since the permafrost itself is not stable as the ground, we need to know more about it, I guess. Um, so where is that? Yes. So there are a lot of things happening with permafrost itself. It basically regulates the water distribution because the water can't go beneath this layer of the frozen ground, so it has to be spreading on top of it. It defines the way how ecosystem looks like and how drainage, how the water flows. And through that, it basically defines ecosystems. Also, it affects the land stability and erosion. We're going to look at that a bit later. Also, it contains large amounts of organic matter. But before going into organic matters and what exactly it is, here the cross section of the layer with the permafrost, and here you can see what's called active layer. So active layer is the ground that's not frozen throughout the year. And then below that, there is a layer of permafrost. And you can see in this cross section that it's just made of many different components, organic, some clay material, and they're alternating with one another. One thing that is used for monitoring this type of behavior of the permafrost is boreholes, like where the temperature sensors installed at the different depth. And the chart on the left shows how the temperature basically tracked throughout the year. So this is the spot for one of the boreholes this type in Yukon. And the mean annual temperature there is about -5 degrees C, average temperature. And there are three different lines you can see here. It's basically plotting your depth on the vertical axis against the temperature on the horizontal. And the lowest temperature tracked goes from -5 at the surface down to 0 at about 10 meters or something. An average is staying below the 0 throughout the year, and the maximum is drifting widely. So we could plot this type of lines throughout many years if we have the observation data, and this is how it looked like for the particular layer, for this particular spot in the central Mackenzie Valley, either Northwest Territories or Yukon. So you can actually clearly see the trend that it's actually warming up, it's melting. What's interesting is that there are some tools that allows you to exploit the data yourself if you are curious. I chose the database I know the best, and that is the GeoYukon database. It contains all this type of the data reported for many different locations, but not for all the seasons, not every year they're functioning. So I want to see if I can show you an example of this live data here. Let's love to do this. So this is the same chart I just showed in the presentation throughout, like from 2009 to 2023, showing minimum in blue, black on average, and the red, I guess, the maximum. And you can see how this changes from 2009 up to 2023, where, well, I'm not even sure if it's a permafrost right now, but what's interesting here is you can actually see the sensors data day by day if the sensors are operating, because apparently here they went down for about a year, and see how they are reading the temperature from different depths throughout the year. So there are very nice tools developed for monitoring that. And I guess we have to rely on them more and more as we trying to evaluate the risks of the changes. I had this slide here just because I had problems with the website, and decided to take a snapshot of how this profile looks like. It's actually worked. That is nice. So because the permafrost retains the water at the upper layer, at active layer and above, it basically defines how the landscape looks like, or for geologists, the geomorphological features. So you can see here the ice wedge polygons. These polygons are about up to 10 to 20, 30 meters in size. you can also see they are created by the seasonal annual variation in temperature as the melting and freezing creates the cracks that are filled with ice, and then basically depositing the soil on top. There is the thermokarst lakes, which I'm going to be mentioning later down the line in this presentation, and also quite extensive river systems. You can see one on here, but this is the satellite screenshot from for this location up in northwestern, like far north in Northwest Territories, with a small road that to the town that you can actually visit from Yukon. It's quite a trip. It's the highway to the end of the world, essentially. And you can see here that the rivers are meandering. They are changing their course because it's easy for the water stream to erode soft ground. And you can see this looping happening all over the place. So landscape seems to be rather flat and unexciting, but sometimes there are things that's called bingo. It's a mountain that's formed in a very interesting way. So imagine you have a lake similar to the one that's shown here with active layer. So the ground that's going through the cycling, freezing and freezing below it, and permafrost lower than that. So at some point, the unfrozen ground can be captured by frozen land on top of it. And because ice, when it freezes, expands, it starts to push this unfrozen ground, and there's not much room for this ground to go but up. And so this upward movement creates this mountains. I think this one is about like at least 100 meters tall. This is something I at some point want to visit. It's quite an interesting feature to see. Um, so this system evolves rapidly and sometimes quickly. There's this chart that shows how thermokarst lakes are forming. So this is this ice wedges that's formed as the ground goes through the cycling of expanding contraction, and they're filled with ice. Then ice starts to melt, and as it melts, it forms the lake. And because the frozen ground took larger volume than unfrozen one, it has to subside, and so we have a lake formation. And as you would expect, this type of the lake formation can have some brutal effects on the infrastructure. Like if there's a road happening nearby, well, then you have to find another way to build the road because the ground is unstable. Also, this is the photo taken from Dempster Highway. So this is the White Horse. Here's the Yukon, and all the way down up to Inuvik, there is a road. It's called Dempster Highway. Um, so ground are unstable, highways are breaking down. What's interesting is that these changes may not be that fast, but in 2024, there was a documented case of actually crater, which means quite an explosive event that happened somewhere in Siberia, where researchers discovered a crater with a 25 meters diameter and about 50 meters in depth, with a lot of materials displaced around it. And it's this creation attributed to melting of a mineral that is formed by methane, CH4, and water. It's called clathrate. So, in a similar manner as it was with Binga formation, where the ground was forced into like smaller and smaller places as the freezing happened. In a similar case here, authors attributed forming this chamber of high pressure that at some point just shot the, I guess, methane through the ground and created this crater with about 200 meters in diameter. So things may evolve fast there. And sometimes we should be ready for that. I am a geochemist. I'm not much into the risk assessment, but from my point of view, we can categorize the risk associated with the permafrost melt in three different categories. One would be sudden onset, localized, similar to I just explained with this crater, though it's a rare event, or more often landslides that's provoked by the melting of permafrost or somehow associated with it. A second type of risk would be the slow onset diffuse. So because permafrost contains a lot of organic matter, as this organic matter decays, it releases methane, and this methane is then not just methane, but also other elements that I'm going to talk later about that may have some uh, that may create a hazard. And the third risk is more cascading compound one. I guess you are aware of the climate change to the same degree that everybody now is. So, and it's basically a self-propelling system in which warming accelerates thaw, which releases more methane. Methane is a very effective greenhouse gas, which accelerates uh, climate change. And so it's creating a feedback loop that goes so quite fast. So I'm not going to talk about the global threat of the um, climate change because we more or less all aware of it, I assume. And I'm going to be focusing more on the first two. So with the first two, sorry about this, there's so-called thaw slump. So this is just a nice illustration that was studied somewhere in Siberia for this thumb, thaw slump, sorry. Um, so similar things happening everywhere across the territories where the permafrost is thawing. It's mostly northern hemisphere. And so this is the evolution of this particular thaw slump through the years. So in 1991, that was quite a deep sort of a trench. But as the ice started to melt and it subsided, it ruined the forest around. So more ground became exposed to sun. So warming up accelerated. And so it started to propagate sideways. And the time of this paper, this thaw slump was about 600 meters across and with a maximum depth of 70 meters. So um, there, here is another view from the Canadian example of this type of landslide. They're not very fascinating to see, but again, the material subsides, it mobilizes the water washes the material down and accelerates the thaw, and it can go off quite fast. But at the same time, there are mechanisms where the additional debris on top of it can somehow stabilize the slope and then keep it in place. They are quite common. This is the small area that I'm heavily focused on in this presentation, at least at now. And Yukon Northwest Territories that is studied well. And this particular paper counted around over 200 active thaw slumps in the area. Some of them are quite close to the infrastructure. Some of these thaw slumps defined as mega slumps, so the structure is similar to the one I showed on the previous slide, where it's expanded by hundreds of meters wide. So it's not an exciting topic, but like landslides are happening anyway. And so another interesting thing is that sometimes these landslides, thaw slump may happen close to the rivers because riverbank provide the change in altitude that is high enough for this to start. And a recent paper showed very close from Whitehorse, the town where I am residing, that this type of landslide can, if it happens in winter, it's causing tsunami, which in winter displaces a lot of ice. So you can see that this is about 200 meters across. Sorry, it should the ice like 2 to 50 meters inland, like moving this types of ice debris throughout the land. In this particular case, again, there was no infrastructure involved, but I'm personally looking very carefully about the perspective of location of the Dawson city, which is northern Yukon. I'm going to zoom out a bit. So, so there were documented prehistoric landslides here, but as you can see in the topography, they have a quite a steep slope across the river from them. And so if there's going to be a landslide, and it seems like the chances are there will, it will displace the river, and the river will go through the town itself. It's the problem that is now currently tracked. There are some monitoring in place, but I didn't know anything about the cases where that would be actually uh, some sort of engineered solutions for that. At least there should be something, I believe, at some point. So now moving back to another type of risk event that is slow onset and kind of diffusing throughout large areas, and that would be an example with the release of contaminants. So metals we don't want to have in our freshwater bodies. So they are releasing over the decades, and they were quite widely they were quite sorry. These metals can be found in are widely abundant in the permafrost. So yeah, this is there's going to be a couple of things about this diagram. So on the right side here, you can see the permafrost with the soil layer in between it. And this particular layer of the soil contains the minerals, as the researchers mapped it here, that are enriched with arsenic and iron. And while the permafrost is stable, these minerals are stable too. And so they're sitting there without interaction with the water. They are kept in place. This diagram on here shows quite a lot. So it's basically showing you a cross section across the ground where you'd see the bedrock, and above that overburden or weather troughs, through which you have the groundwater flow at a certain level with that would be affected by the permafrost above it. And so some of the infrastructure that is present, such as, well, in these cases would be the mines, um, also creates some sort of a threat because in mining, people are working with quite nasty chemicals, and these nasty chemicals are relying on the infrastructure stability to reside in place. And in some cases, they were relying on permafrost itself. So, but as the permafrost thaws, then these elements are becoming available for the groundwater to interact with, and groundwater will pick it up, and then at some point over the decades, bring it to the rivers, well, over the years and decades and thousands of years, bring it to the rivers, and we will have it in our freshwater bodies. So before we move to the next slide, I have a other pool that I would like to start. Here is the same link. Oh, sorry, it's not this one. This one. So different type of reservoirs for the geochemistry are characterized by the amount of elements, metals that they can keep in them. So right now there is a quiz going with the same link, if I understand silo correctly. And it's asking by your estimate how much mercury we have in permafrost. And so it starts with so the atmosphere contains about 5 gigatons of mercury. It is a lot. It's 5 to the times 10 to the power of 6 of mercury just in the atmosphere itself. But how much of it is actually kept in the permafrost. I'm going to give about 15 more seconds before releasing the results. The question is, compared to atmosphere, ocean, and all the soils combined, how much mercury do we have locked in permafrost? So 10 seconds more. 5. Okay. So it's like 300 times more than atmosphere itself. There was a study published relatively recently where researchers evaluated the content of the permafrost, sorry, of mercury in the permafrost by depth from different layers. So the image on the right shows you how much mercury is in like top 30 centimeters, then top meter, top 300 centimeters, top 3 meters, and in bulk in total. And by their estimate, the amount of mercury in the permafrost and active layer is about 1,600 gigatons of mercury itself, just waiting for the release. It's twice the amount of that we have in all the soils, vegetation, ocean, and atmosphere combined. But again, it's going to be released slowly, not instantly. So regarding the release of the contaminants, I would like to focus more on the mining because mining somehow is very active in these regions, but at the same time, it's the way to mobilize contaminants and extract some metals. And also, there are some occasional fuel spills, abandoned equipment left on site. So there are many things happening around it. And this map here shows, again, the permafrost and how mines are distributed throughout um, the northern hemisphere. And you can see that the mining is actually quite active in frozen regions. So it creates a danger. And this danger sometimes are making headlines, like, for example, a couple of years ago, the Little Salmon-Carmacks First Nation raised awareness of the project abandoned mine that they have left on site that is in remediation process that destabilized, oh no, the weather patterns that disturbed by the climate change caused a lot of snow precipitation, and the pond over there that you could see far over on that side would have way more water that can be treated at site. And so the toxic water could be spilled. Luckily, this problem was averted, but it's just to show you that these changes in the Arctic climate, they have lasting consequences. This particular mine operated between 1940s and into 1999, extracting some gold with silver and leaving quite nasty chemicals behind. And so regarding the risks for infrastructures, well, it's just from the snow. Now to more recent example, in the same year, the Eagle Gold Mine experienced a collapse of the heap leach pad. So I have to get back into the mining a bit. For the company, for this particular technology to extract the gold, they are using cyanide. And this cyanide is supposed to interact with ore, so it will dissolve the gold. And then you have a solution to cyanide with gold, which you extract, recycle the cyanide, and extract the gold. So for that, they have a huge piles of the ore stored on site where they are pumping cyanide. It's a very active, very bad chemical, toxic chemical through the ground. And they are relying on many different layers of safety to actually keep it in place. However, in 2024, this happened. You could see the highlighted region where it was a landslide. I'm not saying it's a permafrost triggered because there were many other mistakes done on site, but it was in the permafrost region, and it did continue to the distribution of the groundwater in this heap leach pad itself. So removing this again, small area dislocated first, and then the entire mountain basically slid down. This was about like 4 millions of cubic meters of ore sliding with containing cyanide, going through the barriers that's supposed to contain it. And right now, the territory is not in a good shape with regards to it. Obviously, it raised big concerns from the First Nations on whose traditional territory this mine was operating. The mine went bankrupt. Yukon government stepped up and had to enact some remediation projects. And then right now, I'm working in exploration industry. And I know for myself that there is a general distrust in industry related to anything that would be mined, whether that would be mining itself or exploration, which predates mining by about 20 years. So it created a huge problem. However, sometimes the permafrost can be used for better purposes. That is for another example that I have here. Before going into that, a bit of more details. So this photos on the right is the arsenopyrite. So this is the mineral that contains arsenic, iron, and sulfur, and it's often associated with, in some deposits, it's associated with gold. In Northwest Territories, there was a mine. It's called Giant Mine because it was giant mine. It is very close to Yellowknife itself, the town. But because the environmental regulation back in like mid 20th century was more relaxed than it is right now, the only way they were releasing the gold was to basically burn this arsenopyrite at high temperatures and then basically shooting this arsenic through the smokestacks to the soil nearby. So right now there's quite a lot of the arsenic contaminated soil, and at the end of the lifetime of this mine, they moved some of its soil underground in former mine. And it created another problem because right now there's nothing you can do with this. It's sitting underground. It's going to interact with the water. And at some point it might migrate into the Great Slave Lake, so this is the location of the mine here. This is the town. And this is the Great Slave Lake. It's a large water body that you can see even on this map, but it's not very good. So in special underground chambers, they place this arsenic laced tailings, waste rocks. And the question is what to do with this now. Mining it is also toxic. So the current solution is to freeze it in place. And so in 2004, I believe, there was a project initiated on basically creating an artificial permafrost around it, basically sealing the whole structure. And they installed basically a very long pipes with the CO2 in it that just allows cold air temperature throughout the winter to permeate down to the 100 meters and basically freeze there. And so I'd guess this example here would be a quite telling case of permafrost generating that was used for the betterment of the project that was not conceived properly, unfortunately. So to recap, the permafrost for a long time, as it was formed over the thousands of years, served as a natural barrier. It was accumulating the organic matter that sometimes contains mercury, arsenic, many other minerals and toxic elements, and also the organic matter itself that is now frozen and accumulated there. Then, as it thaws, which is happening with it from time to time, all these things will be released. And also it really lowers the stability of the ground too, which creates the landslides, dangers. In terms of predicting risks, for insurance purposes, I would say there are problems here that there is no historical data. It's happening as we are watching it right now. But at the same time, there are some monitoring methods available, like satellite-related imaging techniques, or similar to the one that I showed you with basically monitoring wells installed throughout the territory. So there are many different types of this risk associated with this, but I myself is more or less optimistic, even though I see quite a lot of problems happening. And with that, yes, thank you for your attention.
Thank you so much. We're having some people clap for you. Do we have
Thank
any
you.
questions? Please feel free to put it in the chat or raise your hand and unmute yourself.
Um, Hi, I actually have two questions for Dr. Yuri.
Sure.
The first question is that, sorry, I just went through your LinkedIn and figured out that you are also an economist. So I have two questions for you. The first question regarding the focus on systematic risk. So from an economic
Mhm.
geological perspective, how do you evaluate the carbon bomb, like you said, the methane, the CO2, things like that, triggered by the permafrost degradation, like degrading,
Degradation,
as a
yes.
potential right black swan event for global insurance market and the northern infrastructure as a whole?
Okay. First of all, I'm an economic geologist. It's a geologist who is focused on economic metals.
Right.
Um, but to your question, it's very diverse. I see the impact on the higher latitude areas to
Mhm.
be higher, to be more significant, because there's going to be a way more changes in temperature happening like further north and further south than from equator. But at the same time, um, the effect is global, but it changes the frequency of um, it changes the weather patterns, and it changes the frequency of the events of the negative events, like drought or floods, or they alternating with one another. So assessing it from the global insurance perspective, the only way I see it is that insurance would like evaluating risk would be more tricky. It would probably rely heavily more on the modeling side than on historical data. And also, it's highly localized events. Like there are some regions that are prone to flood, and they will become more prone to floods. And then I guess it's the question for the companies operating in this particular region: how would they address it? Um, I myself work right now in an industry that is somewhat at the benefit of this climate change because as the glaciers are retreating, there are more deposits to find. And this is something that I'm working with right now. We're looking at the deposit that 20 years ago was basically like under the glacier. So,
Understood. Mhm.
did I address your question?
Yes.
What was the second?
The second one would be like the permafrost. It would act like a geological archive, and based on like beyond the release of like the greenhouse gases, what's the risk of geochemical leaching or the reemergence of the ancient like the heavy metals as these layers thaw?
So, here's the thing: the groundwater itself flows at the different rates in different places.
Right.
And in some cases, the migration itself would take thousands of years. Like there is a particular layer of the groundwater, like in Northwest. I'm thinking about the US, where the groundwater is 100,000 years old, the water itself.
Right.
So it started flowing from Great Lakes down south, and the layer where they intercepted it now is like that far away, and it's flowing that slow. The water they're extracting was at the surface only like thousands of years ago. At the same time, yes, these systems are way more active in terms of how they discharge the water. It's basically water everywhere.
Hmm.
So current policies are basically just avoid certain species of like fish, for example, because they are known to accumulate mercury in them, and just avoid for human consumption. And also, well, from the perspective of the water treatment technologies that we have right now are so well developed that if that would be recognized as a problem, like significant problem, it is easy to address on like the market on market tools. So yeah, but at the same time,
Makes
yes,
sense.
residents should be
Mhm.
related. But the problem is that it has to be monitored first to be addressed. So the awareness comes first.
Gotcha. Thank you.
I have a question in the chat asking if they can reach out to you later for questions. Um, would you be open to
Sure.
them
So
reaching out to you via LinkedIn?
yes, over LinkedIn, or you could see on this thank you image on the right bottom corner my email. You can reach me there.
Okay, perfect. So anyone who has any questions later, feel free to reach him out via email. And if Joe, please go ahead with your question.
Hi. Firstly, I would like to apologize. I won't be able to turn on my camera. I just have a question. You mentioned that there is not historical data available. So currently, I'm actually pursuing my master's in AI. So I was kind of thinking on those lines. So do you think that with advancement in AI, these AI tools will be able to predict and manage the permafrost risks in maybe the upcoming years?
So by referring to, I have a question to you first. By AI, you mean all the methods of machine learning, whether that be supervised, unsupervised, and so forth, right?
Yes.
Or the
Yes.
LLM branch?
Uh, I'm not sure how LLM will
Any?
be really helpful. So yeah, maybe
Well,
initially.
that's the thing. I don't think that LLMs themselves would be much of the use, but using a sophisticated methods of machine learning itself, of which AI is also part of, would
Mhm.
be quite useful because that's basically modeling. Uh, so we have to first of all know more about the ground, and for that, some of the processes are very data intense, and that they would require quite a lot of work to process. I'm going to scroll back to one example here, like this one, for example. I didn't look into the details on how exactly this map was acquired, but I think it may be a combination of the local on-site monitoring versus with satellite data and with like region-wide landscape features identification. So processing large amount of data would be impossible without some flavor of AI. And at that point, that would be like it has to be a tool built for purpose,
Mhm.
which would certainly help. The same way it helped with, I think, folding proteins, uh, resolving like the problem that persisted in biology for a very long time.
Okay. Thank you.
Awesome. Do we have any other questions? Once again, please feel free to put it in the chat or unmute yourself. All right. If not, thank you everyone for joining today. And thank you so much, Dr. Yuri, to you as well for delivering such an insightful and engaging session. It was truly valuable, and I'm confident all of our participants took away a lot from your expertise. We really appreciate you taking the time to be with us and to share your work. Thank you for being a part of today's event, and we'll be in touch for future events and programs.
Hey, thank you for having me. I hope I was not too technical uh, in many aspects, and I was, and like, I tried to. It's hard for me to stay away from the geochemistry and speak in more general terms, but I hope I achieved this goal of mine.
No, yeah, for sure. Most of the students on this call are university students, masters or PhD. So they should be able to grasp it. And like someone mentioned in the chat, they'll research about it
Okay.
more and probably reach out to you after if they have any questions.
Yes. Okay. Thank
Yeah,
you for having me.
definitely valuable. Thank you so much. And thank you everyone for joining today. Please have a great rest of your day.